A P1 alert fires, the clock starts. An engineer must diagnose and resolve a widespread failure while revenue and reputation actively drain. The immediate reaction is to start pivoting between disjointed systems. The engineer checks an observability dashboard, switches to the AWS console, and pulls up GitHub to scan for recent commits. While trying to debug the issue, they pay an administrative tax, manually copying log IDs, taking screenshots of graphs, and pasting context into Jira tickets and Slack channels to keep the team updated. This fragmented manual triangulation burns critical minutes. It inflates mean time to resolution before the actual technical investigation even begins. Distributed cloud architectures generate an overwhelming volume of metrics, logs, and traces during an anomaly. Millions of data points can be emitted every second. Engineers are forced to comb through these distinct data silos sequentially. They hunt for a single failing container or a specific latency spike hidden within normal operations. Resolving these complex incidents requires analyzing data across the entire stack simultaneously, mapping relationships between the application code and the underlying infrastructure. The telemetry needed to pinpoint the failure already exists within the system. What is missing is the connective tissue to correlate it. The primary bottleneck in modern incident response workflows is the cognitive limit of human processing, not a lack of diagnostic data. Any autonomous action requires a trusted, deterministic foundation. This tiered map illustrates Datadog's integration ecosystem, the data layer required to trust automated decisions. Agent-based integrations collect system-level metrics directly from the underlying hosts and containers. Crawler-based integrations authenticate with third-party APIs to fetch cloud provider telemetry, like AWS CloudWatch. Library integrations use the Datadog API to monitor application-level performance and execution traces. Together, these collection methods build a unified, real-time topological map of the entire system. Bits AI SRE functions as an autonomous investigation engine designed specifically for complex environments. It sits directly on top of this established integration ecosystem, granting it direct visibility into every layer of the stack. Bits AI then connects this dataset upward, bridging the gap to collaboration and source control tools like GitHub, Slack, and ServiceNow. Instead of waiting for a human to type a prompt, Bits triggers autonomously the moment a system monitor detects an anomaly. This architecture abstracts away the friction of querying multiple backend databases. It fetches the answers and brings them directly to the user. Passive observability data becomes an orchestrated diagnostic stream that simplifies the initial stages of an investigation. Consider a scenario where a Datadog monitor detects a critical spike in 500 errors on a backend location service. The millisecond that alert fires, Bits AI initiates its investigation. It does not wait for human permission to begin. It immediately reads the specific Confluence runbook linked to the triggered monitor to understand the expected behavior and standard operating procedures. It queries application performance monitoring traces to isolate exactly where the latency or errors are originating inside the specific service. It checks external source control integrations like GitHub, cross-referencing the timing of the errors against any recent code commits. Bits queries its own historical memory, checking past investigations to see if this specific monitor has failed before, and retrieving the exact steps used to resolve it last time. Bits AI executes the same diagnostic checklist a human SRE relies on, but it performs these checks entirely in parallel at machine speed. Using that gathered context, Bits AI dynamically generates multiple root cause hypotheses, evaluating paths like a network failure, a faulty code commit, or a database bottleneck. It methodically queries telemetry to either validate, invalidate, or mark each hypothesis as inconclusive based strictly on the evidence. This data chart isolates the actual root cause, confirming a severe drop in metrics caused by a MySQL connection timeout exhausting the connection pool. Bits formats these findings, embedding the time series evidence graphs and runbook context into a single payload pushed directly to Slack. In parallel, Bits automatically generates a fully populated Jira or case management ticket, documenting the entire incident timeline and diagnostic path. The engineer begins their response with a diagnosed problem and an evidence-backed timeline of the incident. This brings us to the secondary workflow, the conversational poll. Engineers use chat ops to interactively interrogate their infrastructure. Inside the Slack thread, an engineer types a natural language request, asking Bits to check the current Kubernetes pod status for the failing service. Bits AI instantly translates that plain text request into a precise API query against the Kubernetes integration. In that exact same chat prompt, the engineer asks for the current AWS ECS memory utilization metrics. Bits retrieves the data from the AWS crawler integration and formats both the Kubernetes status and the AWS metrics into a rich, interactive widget right inside the chat window. The engineer successfully correlates application health with cloud infrastructure performance without ever logging into the AWS console or the Datadog UI. Standard collaboration platforms like Teams and Slack operate as centralized cross-platform infrastructure control planes. Bits AI's capabilities extend beyond diagnosis. It actively assists in final remediation. When Bits isolates a root cause in code, the dev agent proposes the fix, opening a pull request to correct the syntax. Engineers can also trigger remediation directly from chat. A pod restart command travels to the cluster, executed through Datadog's workflow integrations. This complete cycle, from autonomous detection all the way to conversational remediation, reduces the friction inherent in traditional incident response. The mean time to resolution equation is heavily skewed by the investigation phase. Manual triangulation usually consumes the vast majority of incident downtime. By introducing autonomous orchestration, the Bits AI agent shifts that critical investigation phase from human speed to machine speed. Engineers review validated hypotheses instead of chasing false positives, reducing alert fatigue across the team. It standardizes the quality of incident response. Junior on-call engineers execute with the same diagnostic rigor as more experienced leads. As the system continuously learns from user feedback and historical incident data, every subsequent investigation becomes faster and more accurate. This automation provides every responder with a standardized diagnostic path based on the system's actual topology. The chaotic requirement for manual triangulation and endless tool hopping at the start of an incident has been completely removed. Datadog provides a unified telemetry ecosystem powered by the autonomous orchestration of Bits AI. Implement Bits AI to stop triangulating data, close incidents faster, and get back to building software.